I'm Jane Morris, and in this presentation I'll cover the risk assessment of genetically modified insect-resistant maize, known as Bt maize, for general release and cultivation in southern African countries. But before you watch this presentation, you should first go through the presentation on Bt maize for food and feed use. In that video I give much more background on Bt toxins and how they work, and also much more detail on how to undertake a risk assessment for food and feed use. So today I'll be focusing more on other aspects of a risk assessment that are important to take into consideration before a decision is made to approve general release and cultivation. We'll briefly cover what different types of Bt maize are already grown around the world and also in southern Africa, and then how do we go about assessing the risks for human health and the environment. And we're going to finally go through a full risk assessment for one particular type of Bt maize as an example. Many different types of Bt maize are cultivated around the world. This includes 18 unique transformation events that have been approved in various countries. In some cases, other genes were inserted at the same time and through the same transformation event as the Bt gene, most often genes for herbicide tolerance. In other cases, new combinations of genes have been derived by conventional crossing, often leading to complex stacks with multiple genes. In this presentation, we're not going to focus on stacked traits, but rather on Bt genes in unique transformation events. As you can see from the list on this slide, there are a considerable number of different Bt genes that have been used, each with their own specificity and toxicity profile. South Africa is the only country in the region that has already approved Bt maize events for commercial cultivation. 4 different events have been approved. The earliest was Monsanto's Mon 810, which contains the Cry1AB gene active against lepidopteran pests. Similarly, Syngenta's Bt11, approved in 2005, contains the same Bt gene, but in addition has tolerance to the herbicide glufosinate ammonium. Pioneer's TC1507 has the Cry1F gene, which is also active against lepidopteran pests, and again it also has tolerance to glufosinate ammonium. It was approved for cultivation in South Africa in the year 2012. And finally, there is Mon 89034, which contains 2 Bt genes active against lepidopteran pests. This is the event which we'll examine in detail as we go through a complete risk assessment. So, why did I choose Mon 89034? Well, for a start, it doesn't contain herbicide tolerance genes, and today I just want to focus on Bt maize, since I'll be covering risk assessment for herbicide tolerant maize in a separate presentation. It's also an interesting example because it contains a complex mix of Bt genes, and because it's already grown in South Africa, it is of direct relevance to the southern African region. Mon 89034 can be regarded as a second generation Bt maize, designed to delay the onset of insect resistance. Whereas first generation Bt crops contain a single gene, resistance in the field is starting to become a problem, and some field resistance has already been found in South Africa, mainly attributed to farmers ignoring requirements to plant non-transgenic refugia. So one way round this is to utilize a high-dose strategy to kill the insects and to pyramid several Bt genes with different modes of action into a single plant. So what genes have been used in this instance? Firstly, the Cry1A105 protein, which is a chimeric protein that consists of different domains from Cry1AB, Cry1AC and Cry1F. It was designed by Monsanto to achieve a high level of activity against target lepidopteran pests. The overall amino acid sequence identity of Cry1A105 to Cry1AC, Cry1AB and Cry1F is 93.6%, 90% and 76.7% respectively. The second protein is Cry2AB2, which is also active against Lepidoptera but binds to different midgut receptors. The genes were introduced in a single transformation event using agrobacterium transformation. These are the only genes present because although a gene for resistance to the antibiotic kanamycin was present in the initial transformation event, it was later removed by conventional breeding. And sequence analysis has shown that only single copies of the Bt genes were inserted and no other new open reading frames were present. Expression levels in the different tissues have been determined, and the figures shown here are just for grain, but expression in the other tissues was somewhat higher, ranging from 42 to 380 micrograms per gram in the whole plant for Cry1A 105 and 38 to 130 micrograms per gram for Cry2AB2. Because I already covered food and feed safety assessment of another Bt maize event in a separate presentation, I'm only giving a short summary here of the findings for MON 89034. So, in brief, compositional analysis comparing MON 89034 with its conventional counterpart grown in a range of different environments showed no significant differences in either the forage or the grain. Furthermore, acute oral toxicity studies in mice with the isolated proteins showed no adverse effect at the highest dose administered, which amounted to more than 1,000 times the maximum dose that could be consumed by humans or livestock. There was also no evidence of any allergenicity for either of the Bt proteins. And longer-term feeding studies with MON 89034, in the case of rats for 90 days and 42 days for broiler chickens, showed no adverse effects. So, in conclusion, we could say that no hazards were identified that would make the maize unsafe for use in food or feed. For the environmental assessment, we first want to know how effective MON 89034 will be against the lepidopteran pests that are a problem in the region. The main lepidopteran pests in maize in southern Africa are Bussiola fusca, or maize stalk borer, and to a lesser extent Chylopotellus, which is also sometimes known as the sorghum stem borer. MON 89034 has been shown to have more activity against Bussiola than plants with the Cry1AB gene alone. Now, in South Africa, there are already some instances of Bussiola resistant to Cry1AB, so this could really be an important tool to manage resistance. One concern about Bt crops is whether they have a negative effect on beneficial non-target insects. The long-standing debate about monarch butterflies in the States is a case in point. And there are, in fact, some non-target lepidopterans that feed on maize in southern Africa, and I list some of them here on this slide, but none of these are regarded as beneficial. In terms of other non-target organisms, the Bt proteins are specific to Lepidoptera, and tests on coleopteran and hemipteran species showed no toxicity, so no negative effects are anticipated. Studies on soil organisms also haven't shown any negative effects, and both proteins are 90% degraded in soil within a maximum of 19 days, so there should be no build-up in the soil. To check the lack of effect on a range of non-target organisms, tests were also carried out on a range of indicator species of non-target invertebrates that might be found in maize fields, including honeybees, both the larvae and the adults, the minute parrot bug, the ladybird beetle, a parasitic wasp, earthworms, and collembola. No adverse effects were seen for any of these organisms exposed to the Bt proteins. In addition, to check the effects on aquatic organisms that might be exposed to pollen from the Bt maize, the invertebrate Daphnia was chosen. Again, no adverse effects were seen. Field trials were carried out with MON 89034, originally in the United States, but later also in South Africa. Its performance was compared with its near isogenic conventional counterpart, and no changes were seen in phenotypic or agronomic performance other than the introduced traits. There was also no increase in weediness or invasiveness potential. One concern for general release of GM crops is the potential for gene flow, either to wild relatives or to conventional non-transgenic plants. In this case, maize has no wild relatives in southern Africa, so horizontal gene flow is not possible. Of course, gene transfer to conventional maize is possible. However, maize pollen is heavy, so it doesn't travel far, and it's only viable for 1 to 2 days. Extensive tests have shown that there is less than 0.5% cross-fertilization at distances over 50 meters. So by keeping the GM maize at least 50 meters from conventional maize, any GM content in the conventional maize would be well below a threshold of 0.9%, which in Europe and some other countries is a level above which labelling is required. In South Africa, the threshold for labelling is higher at 5%. This, of course, is not an issue of safety, but rather an issue of consumer rights to know, since gene transfer to conventional maize would not result in adverse effects to human health or the environment. Another concern for Bt crops is that the target lepidopteran pests could develop resistance to Bt. As I said earlier, the inclusion of 2 Bt genes in MON 89034 is one way to delay the onset of resistance. However, in addition, any release needs to be accompanied by a resistance management strategy and ongoing monitoring. In all cases, there is a requirement for a non-transgenic refuge as a standard measure, but in this case the size of this might possibly be reduced because of the presence of the 2 Bt genes. Compliance monitoring is still essential, and it's also essential to explain to farmers the importance of the refugia. But these are all issues that I'll go into in a separate presentation on managing resistance to Bt. So overall, having gone through the risk assessment, we can state that no hazards were identified that would lead to significant harm to humans or the environment, and that the likelihood of any harm materializing can be considered negligible. The overall risk is therefore also negligible, and from this perspective, regulators could be confident that they could give approval to general release of MON 89034. There is, however, one more aspect that might be considered, and that is the issue of socio-economic impacts. Every country decides according to their legislation whether they will take socio-economic impacts into consideration, and of course these may be either negative or positive. A lot has been written about the difficulties of carrying out socio-economic assessments, particularly ex-ante assessments, that is ahead of any approval. There is no clear methodology, and while many countries include socio-economic issues in their legislation, few have a clear approach as to how to go about it. However, now that Bt maize has been introduced in many countries, including South Africa, there is starting to be a growing body of ex-post data concerning socio-economic impacts. On balance, we can say that the findings are that Bt maize has had an overall positive effect. Measurable benefits include increased farm income, higher yields, and decreased use of pesticides. In the case of small-scale farmers who do not always have adequate protective equipment for spraying, the decreased use of pesticides is particularly important from a health perspective. So we can reach the final conclusion that MON 89034 can be safely cultivated in southern Africa. Note, however, that each Bt event should be assessed on a case-by-case basis. However, the methodology that I've shown you here can be easily followed for other events. Thank you.